KPIs. Key performance indicators, or KPIs, are critical tools used to measure success in semiconductor manufacturing operations. These indicators help organizations track performance, ensure product quality, improve operational efficiency, and control costs. In semiconductor environments, performance KPIs may include throughput, uptime, and cycle time, key elements that reflect how well equipment and processes are running. Quality KPIs monitor yield, defect density, and reliability, helping teams detect issues early and maintain high standards. Efficiency metrics, such as overall equipment effectiveness, OEE, look at how well resources are used in production. Cost KPIs track spending, waste, and productivity per dollar spent, all vital to maintaining profitability in a competitive market. By closely monitoring these KPIs, teams can identify areas for improvement, set goals, and drive continuous optimization across operations. Understanding and applying KPIs is essential to achieving consistent, high-performing semiconductor manufacturing outcomes. What is semiconductor manufacturing? Semiconductor manufacturing is the process of creating computer chips that power everyday devices, from smartphones and laptops to medical equipment and cars. These chips are built using silicon wafers, which are embedded with transistors and circuits to process and store information. The process begins with design and planning, where engineers create detailed blueprints and specifications. Next comes wafer production, involving the preparation of ultra-pure silicon wafers. In the fabrication stage, complex layering and etching steps are used to build the intricate circuitry. Finally, the chips undergo testing and assembly, which ensures functionality and packages them for integration into final products. With more than 300 process steps and current technology reaching the 3 nanometer scale, precision is critical. KPIs matter in this $600+ billion global industry because they help manage complexity, maintain precision, and ensure that each step adds value without introducing defects. KPI overview. Key performance indicators, or KPIs, are measurable metrics that reveal how well a company is achieving its key business objectives. Think of them as a report card for your operations. In semiconductor manufacturing, KPIs fall into 4 main categories. Production KPIs track yield, throughput, and cycle time to gauge output and efficiency. Quality KPIs monitor defect rates and first-pass yield to ensure products meet high standards. Cost KPIs focus on manufacturing cost per unit to maintain financial performance. Equipment KPIs include OEE, overall equipment effectiveness, along with uptime and efficiency, all of which reflect how well machinery is utilized. KPIs matter because they provide visibility into what's working, offer direction for decision-making, and support improvement through ongoing optimization. The success formula is simple. Combine clear goals with accurate data and regular review to achieve sustained results. Ultimately, KPIs transform data into decisions, and decisions into measurable business outcomes. Production efficiency KPIs. Production efficiency KPIs are key to understanding how effectively semiconductor manufacturing lines are running. One of the most important metrics is yield rate, which measures the percentage of good chips produced out of the total. These are the chips that successfully pass quality testing. A yield rate under 70% is considered poor, between 70% and 85% is good, and anything above 85% is excellent. The current industry average sits right at 85%, setting a high benchmark for operational excellence. Another essential KPI is cycle time, which tracks the total time needed to manufacture one wafer from start to finish. This includes all steps, from wafer prep to final testing. A faster cycle time is typically between 6 to 8 weeks, while most fabs operate within 8 to 12 weeks. Reducing cycle time and improving yield leads to higher throughput, better cost efficiency, and stronger competitive performance. Production efficiency KPIs. Production efficiency KPIs are key to understanding how effectively semiconductor manufacturing lines are running. One of the most important metrics is yield rate, which measures the percentage of good chips produced out of the total. These are the chips that successfully pass quality testing. A yield rate under 70% is considered poor, between 70% and 85% is good, and anything above 85% is excellent. The current industry average sits right at 85%, setting a high benchmark for operational excellence. Another essential KPI is cycle time, which tracks the total time needed to manufacture one wafer from start to finish. This includes all steps, from wafer prep to final testing. A faster cycle time is typically between 6 to 8 weeks, while most fabs operate within 8 to 12 weeks. Reducing cycle time and improving yield leads to higher throughput, better cost efficiency, and stronger competitive performance. Quality KPIs. Quality Key Performance Indicators, or KPIs, are essential for monitoring and improving semiconductor manufacturing outcomes. One key metric is defect density, which measures the number of defects per square centimeter of wafer. A value below 0.1 is considered excellent, indicating minimal process variation or contamination. Between 0.1 and 0.5 is acceptable, but caution is needed. Anything above 0.5 is poor, suggesting significant quality issues. Here, the defect density is right at 0.1, on the border between excellent and acceptable. Lower is always better, as fewer defects increase yield and reduce scrap. The second metric is rework rate, which is currently at 8%. This represents the percentage of chips needing additional processing to meet quality standards. The target is under 5%, so 8% is above threshold. Rework leads to a 40% increase in time, a 60% rise in costs, and 35% more resource usage. High rework directly drives up production expenses and reduces throughput efficiency. Quality KPIs. First pass yield, or FPY, measures the percentage of chips that pass all tests on their first attempt without requiring rework. A high FPY indicates process stability and good quality control. Here, FPY stands at 92%, which falls into the good range of 85–95%, but below the target of 95%. Achieving excellent status requires a yield greater than 95%, which minimizes delays and production costs. Anything below 85% is considered poor, indicating frequent issues during fabrication or testing. Next is customer returns, currently at 0.02%. This metric tracks defective products returned by customers. The target is less than 0.01%, so improvement is needed. The Six Sigma Quality Framework classifies defect levels. Six Sigma means world-class quality with only 3.4 defects per million, while 5 Sigma is excellent. At 5.2 Sigma, the current performance is within the industry target of 5 to 6 Sigma, but still leaves room to drive down customer returns and boost trust, reduce delays, and minimize cost. Cost and financial KPIs. Cost and financial KPIs are essential for managing manufacturing efficiency and profitability. The cost per wafer metric represents the total manufacturing cost for each 300mm silicon wafer. Currently, the cost is $1,250, which exceeds the target of $1,200 by $50. This overage is significant in high-volume production. Cost breakdown shows 35% from raw materials, 25% from labor and overhead, and 40% from equipment depreciation. Managing these components effectively is critical to staying on budget and remaining competitive. Next, the equipment cost measures the total hourly cost of operating semiconductor manufacturing equipment. It currently stands at $1,150 per hour. This includes $1,200 per hour in depreciation, $350 for maintenance, $200 for utilities, and $100 for consumables. The equipment utilization rate is 78%, which reflects how efficiently the tool is being used. Higher utilization improves cost efficiency, while idle time drives up the per-wafer expense. These KPIs help identify cost drivers and guide improvement strategies. Cost and financial KPIs. Cost variance shows the gap between planned and actual spending. The current variance is plus 4.2%, meaning costs have exceeded the budget by this margin. While Q1 was favorable at 1.2%, indicating underspending, Q2 shifted to plus 2.1%, and Q3 rose further to plus 4.2%. This upward trend suggests a pattern of escalating costs that must be addressed. Persistent variance can reduce profit margins and erode financial flexibility, making budget adherence a key operational priority. Return on investment, or ROI, evaluates the efficiency of capital spending. An 18.5% annual ROI indicates strong performance, especially since it exceeds the industry benchmark of 15 to 20%. The total investment of $2.8 billion includes fab construction and equipment. Annual returns are $520 million, calculated as revenue minus operational costs. The payback period is 5.4 years, with the break-even point occurring in year 3.2. The 10-year net present value stands at $1.2 billion. These figures demonstrate the project's financial health, driven by revenue growth, productivity gains, and cost control. Equipment performance KPIs. Overall equipment effectiveness, or OEE, is a comprehensive metric that combines availability, performance, and quality. It is calculated using the formula OEE AXPXQ. Here, availability is 92%, performance is 89%, and quality is 96%. Multiplying these gives an overall OEE of 84%. This places the equipment in the good category, which ranges from 65% to 85%. To reach world-class status, OEE must exceed 85%. The current result is close, but there's still room for fine-tuning process efficiencies, cycle times, or maintenance strategies to improve. Equipment uptime reflects operational availability and currently stands at 92.3%, just below the 95% target. Unplanned downtime accounts for 3.2% and planned maintenance for 4.5%. These downtime events impact cost and productivity. The financial cost of downtime is $85,000 per hour, and it results in the loss of approximately 650 wafers. Keeping uptime high is critical to ensuring throughput, minimizing delays, and optimizing resource utilization. Equipment performance KPIs. Overall equipment effectiveness, or OEE, is a comprehensive metric that combines availability, performance, and quality. It is calculated using the formula OEE AXPXQ. Here, availability is 92%, performance is 89%, and quality is 96%. Multiplying these gives an overall OEE of 84%. This places the equipment in the good category, which ranges from 65% to 85%. To reach world-class status, OEE must exceed 85%. The current result is close, but there's still room for fine-tuning process efficiencies, cycle times, or maintenance strategies to improve. Equipment uptime reflects operational availability and currently stands at 92.3%, just below the 95% target. Unplanned downtime accounts for 3.2% and planned maintenance for 4.5%. These downtime events impact cost and productivity. The financial cost of downtime is $85,000 per hour, and it results in the loss of approximately 650 wafers. Keeping uptime high is critical to ensuring throughput, minimizing delays, and optimizing resource utilization. Innovation and time to market KPIs. Research and development, R&D, is critical for staying ahead in semiconductor technology. R&D investment here stands at 18.5% of total revenue, which is well above the industry average of 15.2%. This indicates a strong focus on innovation. The $4.2 billion in annual R&D spending is allocated across process technology, 45%, product development, 35%, and equipment innovation, 20%. With 850 researchers on staff and an output of 28 patents per month, the innovation pipeline appears strong and sustainable. New product introduction, or NPI, is another key indicator, with a current success rate of 78%. Out of 18 product launches, 14 have been successful, while 4 failed. Success is measured through 3 key factors: market acceptance at 85%, technical performance at 92%, and cost target achievement at 73%. These figures suggest strong technical capability and market alignment, though cost discipline could be improved. timely innovation and efficient product rollouts are essential to competitive advantage. Innovation and time to market KPIs. Time to market tracks how long it takes to move a concept into full production. The current average is 24 months, which represents a 20% improvement from the previous average of 30 months. This timeline includes 4 main phases. Research and design takes 8 months, prototyping takes 6 months, testing and validation takes 5 months, and the production ramp adds another 5 months. Faster time to market is crucial in staying competitive, meeting customer demand quickly, and maximizing ROI on innovation. The technology node metric indicates the current process technology level, which is 3 nanometers. The roadmap shows 3 nanometer production is scheduled for 2024, followed by 2 nanometer development in 2025 and 1.4 nanometer research in 2026. This roadmap reflects aggressive scaling and process advancement. With 256 patents filed, 12 strategic partnerships, and 95% of tech goals achieved, the innovation pipeline remains strong. There are currently 47 active projects under development, demonstrating a healthy pace of forward-looking technology investment and execution. Summary and implementation. To ensure operational excellence and drive continuous improvement, organizations must track 5 key categories of KPIs. The first is production efficiency, which includes metrics like yield, overall equipment effectiveness, OEE, and cycle time. These indicators help evaluate how well production lines are performing and where delays or inefficiencies may occur. Improving production KPIs leads to faster throughput and greater output per tool. Next is quality excellence, measured through defect rates, first pass yield, FPY, and customer returns. These KPIs highlight the ability to meet specifications consistently and avoid costly rework or warranty issues. Higher quality reduces waste and boosts customer satisfaction. Cost and financial KPIs, such as cost per wafer, ROI, and cost variance, help manage resources effectively and protect margins. Equipment performance focuses on uptime, mean time between failures, MTBF, and maintenance efficiency. Reliable equipment minimizes disruptions and supports high-volume manufacturing. Finally, innovation KPIs track R&D investment, new product introductions, and time to market. Together, these categories form a complete framework for sustaining competitiveness and growth. Summary and implementation. A structured roadmap is essential for effective KPI implementation and long-term results. The process begins with a baseline assessment in month 1. This involves analyzing the current state of operations and identifying performance gaps that need to be addressed. Next, during months 2 and 3, comes KPI selection and setup. This includes defining the right metrics and setting up systems for accurate and continuous data collection. By months 4 and 5, the focus shifts to dashboard and monitoring. Real-time tracking tools and alert systems are introduced to provide visibility and support fast response to deviations. Finally, from month 6 onward, teams engage in optimization and training to drive process improvements and build team capability. The expected benefits are significant. Yield typically improves by 5–15%, while cost reduction ranges from 10 to 25%. Cycle time can decrease by 20%, and OEE often increases by 10%. With successful deployment, organizations can expect a 300–500% ROI within 18 months. Summary and implementation. Successful KPI implementation depends on a few critical success factors. First, strong leadership is essential. Executive sponsorship helps prioritize KPI initiatives and ensures follow-through. Second, data quality is a must. KPIs are only as useful as the accuracy and timeliness of the data that feeds them. Third, training ensures the team understands both the metrics and the systems supporting them, building competency across all levels. Finally, fostering a culture of continuous improvement reinforces a mindset of adaptation and optimization. For next steps, it's best to start small. Begin with 3 to 5 critical KPIs that can drive immediate value. Secure leadership buy-in early to gain the necessary support and resources. Next, invest in analytics. Having a robust data infrastructure enables real-time visibility and decision-making. Finally, focus on action. KPIs should not just be tracked, but actively used to drive continuous improvement. With these steps, you can begin transforming your fab toward manufacturing excellence.